Yes, is the screen visible?
Yes, sir.
Okay. Actually, this is the wrong lecture. Yes, this is the correct lecture. Yes. Okay. So until now, we have discussed what are the characteristic features of algorithms. Anyone who can just name the characteristics of an algorithm that are required? What are the specific requirements or desirabilities in an algorithm? Okay. So that is what we are going to see. Just a second. Yes. So if you remember, then the characteristics of several characteristics of an algorithm that are desirable are input. There should be one output. Okay. There should be finiteness. That is, it should end in limited number of steps. Okay. Then there should be correctness and there should be effectiveness. Finally, I had added something which is called machine independence. Okay. So yes, one more is there, definiteness. There should not be any ambiguous statement. Okay. So yes, all these are the desirable characteristics of an algorithm. These are all the things you require when you write an algorithm. If these all things are present, then the algorithm is desirable. When I say desirable, then more people would want to use it. Okay. Like someone designed the RSA algorithm, that is the cryptography algorithm, and today it is one of the most used cryptographic algorithms in the world. Okay. So similarly, why? Because all these things are present in RSA. Okay. So yes. So why the point of discussion? The point of discussion is we will come to the characteristic called correctness today. Okay. So what do you mean by correctness and how we can actually evaluate if any algorithm is correct or it is wrong? Okay. So there are three ways actually to find out if an algorithm is correct or wrong. Okay. So the mathematical way of doing it is known as the induction method. Okay. And if you can prove it theoretically, then there are two methods where one is known as the method of counter example. Am I audible to you all? Because I am not feeling well, and if I am not audible, then let me know.
Yes, sir, audible.
The second thing after the counter examples is your prove by your loop invariant method. This is a very difficult method. Okay, I have already told this to you. But the loop invariant method, nevertheless, is one of the methods that is used to prove the correctness of algorithms that basically use the concept of iteration. Okay, iteration means loop. Okay, so yes, when you have the concept of loops or you have in your iterations, in those conditions, the loop invariant based proof method is used. Nevertheless, it is one of the difficult methods out of all three. Okay. So yes, now when we come to the counter example case, this you have to think a lot. Okay. So whenever you are going to find a counter example, suppose an algorithm is given to you. Okay. And what do you do here? You want to prove the correctness of this algorithm. But in fact, we will prove the incorrectness of the algorithm. If you can prove that the algorithm is incorrect, then it is not correct. Okay, so yes, I cannot prove the correctness, but I can prove the incorrectness. How? Through one example that will prove the proposed approach is not optimal and that there exists another algorithm that produces a better result. Okay. So what happens here? If you can show that there is at least one example, okay, one case where you can prove that the proposed approach is not optimal. That means that the algorithm that we are talking about, it is not optimal. If you can show it through example, then that example is called as a counter example. You are countering the correctness through this example. Okay. And that there exists another algorithm which produces a better result for this counter example also. Let us consider this with an example. Let there be algorithm A1 and let there be algorithm A2. Okay, let us consider the concept of vortex coloring that I have discussed already with you. Okay, so yes, here suppose A1 takes 3 colors and A2 it takes 2 colors. Okay, so yes, now in this case, if I can say that this is not the optimal algorithm, how can I show it? I can show that there is one case where A2 must take 3 colors. So we have already told that A2 is an algorithm that will always take 2 colors. But now, if I can find a counter example, okay, if I can find a counter example which shows that yes, this A2 must require 3 colors, okay, in that condition, what will happen is that your A2 is no more the most efficient algorithm. But at the same time, this statement also says that there is another algorithm A3, okay, which will take 2 colors for this counter example also. For all the examples, it will take 2 colors. And also for the counter example, now it will take 2 colors only. So now we can say A3 is the most optimal algorithm. Why? Because there is one case where A2 failed. Okay, but we have not found such a case for A3 yet. Of course, you can find a counter example if it exists for this algorithm also. Okay, and then you can prove that yes, A3 will also take 3 colors for a certain graph. Okay, for a certain example, for a certain case. Okay, so all these things are comprised of your counter example. And next, when we come to the method of induction, that is a very mathematical way of showing that your algorithm is correct. Yes, 3 things have to be verified. One is the base case. Then you will make some assumption. And then you will prove the assumption through a hypothesis. Okay, so this is the simplest case that will always be true. Okay, then we come to the case of assumption where we assume that it will be true for some value called n. Okay, and if we can prove that for the base case it was true, for the assumption we took that we assumed that it is true, now if we can prove that it is true for n plus 1, Now it is also true for n. Okay. So yes, this is how we are going to prove through induction. So today's topic, where we are going to prove the correctness of an algorithm, will start with the simplest of counter examples. Okay. So now we will go through two counter examples that show how you can find counter examples for an algorithm. Okay. And using those two examples, we will actually see how our algorithm basically performs. Okay. Okay. So now, if I just go through the outline, this is what we are going to learn today. This is the important point. Okay. So these are the two examples that we are going to see, and we are going to see how you can prove that two given algorithms, for these two examples, they are always incorrect. Okay. So we will find counter examples to show that these algorithms are incorrect. Okay. Next, in the next lecture, we'll go for loop invariant. This will take us, I think, one class. And after that, we will go for the induction method. Okay. So yes, I want you to concentrate in today's class. Sorry. Because the example that we are going to see is a bit confusing. Okay. And then we have to also find the counter example. Okay. Yes. Why correctness should be verified? Now we are going to find out the correctness of an algorithm. Now you will ask me, am I audible to you all?
Yes, sir.
Yes, sir.
So yes, now when we are going to check the correctness, so now we are concerned that why correctness? Why do you need to find the correctness? Why do you need to prove even that your algorithm is correct? I am showing it that for 99 cases, it is giving the correct answer. Then why do I need to prove the correctness of this algorithm? Okay. So now the first point itself makes the topic clear. It is seldom obvious that whether a given algorithm correctly solves a given problem. Now, if I just give you a random algorithm, now I say, yes, just look at this algorithm and tell me this is the algorithm for swapping two numbers. Now, see, if you remember things, then this might be wrong. Okay, you might tell that, okay, these formulas are wrong. But now just look at this algorithm and can you tell me if this will give the correct result or not? No, it is very difficult. So just look at the algorithm and tell if it is a correct algorithm or if it is a wrong algorithm. But at the same time, we also need to show that this algorithm is correct. So that is why there are formal methods that can prove that the algorithm is correct. Okay. So yes, once we have shown that this algorithm is correct through this formal method, nobody can question us. Okay. Once you prove through induction that the algorithm that you have written is correct, then nobody is going to ask questions on the process of math. Okay. So that is why we can correctly assume that yes, some method is required to prove the correctness of algorithms. Okay. Correct algorithms usually come with a proof of correctness. Okay. Which is the explanation. A POC is always given. Whenever you write algorithms, when you go forward, you write research-based algorithms or you write your software-based algorithms, a proof of concept or proof of correctness is given. Okay. So that proof of correctness if you are asked to submit the proof of correctness, how will you do it without understanding how the correctness can be found out? Okay. So the best way to prove an algorithm incorrect, this is important, okay, is to produce an instance in which it yields an incorrect answer. Okay. So basically, this is the concept of counter example. Okay. Where we are going to prove that yes, there is one case where this algorithm will fail. And if this algorithm will fail, this is the instance where we can declare that the algorithm is incorrect. Okay. So yes, let us go into the details of your counter example using the problem of robot tour optimization. Okay. So what is a robot and how it will optimize its tour? Why it will optimize its tour? Okay. So suppose there is a robot and this robot has a robotic arm. Okay. And this arm can do a lot of things. Okay. So now let this arm is equipped with a tool, welding tool or something. Okay. Suppose a soldering iron there. Say. Okay. So now this is the robot. And this robot has an arm. Okay. That arm is equipped with a soldering iron. Okay. In manufacturing circuit boards. Now, if you have seen a circuit board that is in your home, you would see that there are several points in the board. Okay. Now, these points have to be soldered like this. Something like this. Okay. And then a circuit will be formed. Okay. So if you would have seen the back of the circuit board, this is how it looks like. So the soldering of wire should be there. Okay. So now we are given a robotic arm that is equipped with a soldering iron, and in manufacturing circuit boards, all the chips and other components must be fastened into the substrate. Now you would have seen there are several things like this, and this particular thing is called the substrate. Okay, VI board. Okay. So once you have this substrate, over this substrate, you will place all the components. Okay. So yes, these components have to be placed in the board through the process of soldering. Okay. That is why we use a soldering iron. So if you imagine the volume of circuits that are produced, it will be huge. So doing it manually will take a lot of time. Okay. So now our problem statement says that yes, this circuit has to be designed by this robot. Okay. So now, suppose this is the robotic arm. Okay. Soldering iron. Okay. And the iron must now move to this position. It will solder it here. Now, then it will move here. Then these 2 points will be soldered. Next, the soldering iron will come here. It will solder something here. It will go here, come here. Again, it will go here. It will come here. Okay. So now if I ask you the question, okay, so write an algorithm so that the robot solders each component with minimum travel distance. Okay. So now our objective is which point should be visited first. If this is 1, 2, 3, 4, 5 and 6. Okay. So now will you visit the points 1, 2, 3, 4, 5, 6? Will you visit them 6, 5, 4, 3, 2, 1? And if this is the distance between 2 points, such that our distance is minimized. Okay. So now you have to find an algorithm such that you have to now find the sequence of points which will be visited such that the distance that is traveled by the robotic arm is minimum. Why you want the distance to be minimum? You want the distance of the robotic arm to be minimum because your cost of moving the robot should be minimized. Okay. So we want to minimize the cost of moving the robot. Okay. So if we move this robot from point 1 to point 2, okay, the distance suppose between the board is 30 micrometers. Okay, so 30 millimeter, let us say. Okay, now similarly, if I move to point 3 now, the distance will become something like 20 mm. Okay, this distance. So now if you see, the cost of going from here to here will be more than the cost of going from here to here. Why? Because here the distance is more, here the distance is less. Okay, so now that is why we want to minimize the distance while the robot moves. Why? Because the more distance the robot moves, the more cost we have to pay. Okay, and that is why we want to shoulder all the points while the robot makes minimum movement. Okay, so that is the objective of the problem. Yes, is it clear or any doubt? Any doubts until now? Am I audible to you all?
Yes, sir, audible.
Okay, so yes, if you don't have any doubts, so let us move on to the solution sketch. How we can form a solution for this problem such that all the points are visited but the robot travels minimum distance. Okay, so yes, now if I just want to find a solution, let us look at a solution sketch of it. Okay, a solution sketch basically means the informal steps of how you can go, how you are going to find the solution. Okay, to program the robot arm for this job, we must first construct an ordering of the contact points so that the robot visits. I told you the ordering. It might be 1, 2, 3, 4, 5, 6. So the robot will visit point 1, then it will visit point 2, point 3, point 4, so on. If it is 5, 4, 3, 2, 1, 0, then the robot might move from here to here, from here to here, from here to here. But what we are more concerned here is the robot should not move like this. It goes left, then it again comes right, it visits another point. If you see, then here unnecessarily it is wasting that distances. Okay, it is going to one side, but it is not completing everything on one side. Again, it is coming back to the other side. Again, from this side, if we go here, there is another point here. The robot again comes back to this side. So if it moves like a pendulum, then that is not required. Why? Because it can go to one side, it can complete like this, and then it can come to the second side, and then it does like this. So here, the things are wasted. But if you see, here the things are optimized. Okay, so that should be our intuition. Okay, so that the robot should not waste its movements unnecessarily. Okay, so yes, now let us look at the solution that can work. Okay, this constant is basically what we have discussed is the distance. We have to minimize the distance, so that is the constant of the problem. Okay, so yes. Now, if we formally define the problem, I have already told you what is the formal definition and what is the informal definition. So when you define a problem mathematically, then it is known as the formal definition of a problem. Okay, so yes, the problem is robot tour optimization. Okay, and what is the input? The input to this problem is a set of points where we need soldering. Okay, these are the points we will need soldering. Okay, and what should be the output? The output should be the shortest cycle tour that visits each point in the set S. Okay, so now the shortest cycle tour, which means what do you mean by cycle tour? We have already discussed in the first class itself what is a cycle. Okay, so I start at one point, I visit all the points, then I again come back to the starting point. So this is a cyclic tour. When the starting and the ending points are same, then such a path is known as a cycle. Okay, so here we are going to go for a cyclic tour, but the constraint here is the distance should be minimum. That is the constant that we are going to follow. Now you will say that yes sir, this is a very simple problem, I can solve it in 2 minutes. Yes, how? I know the distances. These points also have distances. Okay. So now you'll say, I will write 1, 2, 3, 4, 1, 2, 3. I'll write 3, 2, 1. I'll write 2, 1, 3. And all those combinations I'll write. Okay. Once I write these combinations, I'm obviously going to add their distances. From 1 to 2, what is the distance? From 2 to 3, what is the distance? Suppose this distance I'll get 7. Then I'll do this. I'll get 8. This distance I do, I'll get 6. Some distance I'll do, I'll get 5. I compare all the distances. I know sorting. I will compare all these distances and I will say, yes, this is the minimum distance. So yes, something like 3, 1, 2 should be followed. Okay, something like this. Okay, yes. Are you able to follow this? So this is basically known as the brute force method. So how many combinations will be there here?
Excuse me, sir. Sir, your voice is,
yes.
Sir, your voice is not clearly audible.
Now? Is it audible now?
Yes, sir. Now it's audible.
Let me know, okay? If it is not audible in the middle, just let me know. Okay. So yes. Now if I was just saying that now somebody what he might do, he might write down all the combinations of these points or all the permutations. 1, 2, 3, 2, 1, 3, 2, 3, 1, 3, 1, 2, all the combinations. Okay, all the permutations which are basically 3 factorial combinations will be there. Okay. So yes. Now if I just go on increasing the value of n, let n be hugely large. So do you think this kind of a solution is possible? This brute force method, or just writing down all the values and then adding their distances. We will add their distances to find, let us this be 7, 6, 5, 3. Now I can compare the distances and I can say, yes, the robot should visit point 3, then it should visit point 1, then it should visit point 2. Okay. But do you think when n is equal to very, very large, will this strategy work? No. This strategy will actually not work. Okay. Why? Because then there also will be n factorial combination. Okay. And to handle this n factorial combinations, when n is very large, is very difficult to a greedy approach, such as this, or a brute force approach. Okay. So what we will do is we will design a problem, we will design a solution which is called the nearest neighbor heuristic. Am I audible clearly?
Yes, sir.
Okay. So yes, the nearest neighbor heuristic. Okay. So given a set of points You have to understand this algorithm, so you have to concentrate. Okay. So given a set of points, now we will select some point as the starting point P. Let me just change it. Starting point which is called P0. Okay. So from this P0, now I will find which is the nearest point. I know the distance. Okay. I know these distances. So I will now find the nearest point. Then from this point, now again the nearest point I will find. Again from this point, the nearest point I will find. Okay, I will go on doing this until all the points are visited. Then from the last point, I will connect the starting point. Okay, let me just show it to you once more. What the algorithm will do. Okay. So these are the points that we have. Okay. So the algorithm says select some point as P0. Some point, you can take any point. Okay. Now from this point, find the short point that is at this least distance. Okay. So from this point, if I find the least distance point, let this be the least distance point. So from here, this is called now P1. From P1, I have to find the least distance point. Okay. From here, I will connect this. Okay. Now this will become P2. Okay. So from here, again, I have to find the point with the smallest distance. Okay. So let this be this. Okay. Just remove this one. Okay. So now from here, what I can do is now from this point, I will find any unvisited point which is at a shortest distance. If you see, there is one unvisited point which is this. Now this is called as P4. Okay. So now if you see, the definition was it should be a cyclic tour. Okay. So the point from which it started, it should come back to that point which is P0. So now from P0, we have to just connect. From P4, we have to connect P0. Once we connect P4 to P0, this is what the nearest neighbor algorithm will return. Why nearest neighbor? Select a point, find its nearest neighbor. Select another nearest neighbor. Go on building the cycle by finding the nearest point. Once you reach the last endpoint, connect both the endpoints to complete the cycle. Okay. Yes, that is what it is saying. Start from some point P0, we walk to its nearest neighbor called P1. From P1, walk to its nearest unvisited neighbor, which is called P2. Okay. So until we reach all the unvisited vertices, we would have created a cycle without the last point. Okay. So at this point, we repeat this process until we run out of unvisited points. Once we run out of unvisited points, now we return back to the last point by connecting a wire and completing the cycle. Okay. This is the algorithm nearest neighbor. What it takes a set of points in a plane. Okay, that is why the input here is P. You have to define that also. We have already defined, the formal definition is present in the previous slide. Okay. And then the first, this should be like this. Okay. Whenever an algorithm is given, try numbering it. Okay. So yes, pick and visit an initial point P0 from P. Pick any point as P0. Okay. Now, P is equal to P0 and I is equal to 0. So this P is our pointer for point and the initial point is P0. Okay. Now we take the point loop variable or iteration variable which is called as I, while there are still unvisited points. Okay. So until there is at least one unvisited point, this loop will execute. Okay. Once we have visited all the points, this loop will stop executing and we will come out and this statement will be executed. Okay. So now when there is an unvisited point, I is equal to increment the value of I. I is equal to I plus 1. Select Pi to be the closest unvisited point to Pi minus 1. Now visit Pi. Let us just dry run this example. Okay, so we are given a set of 5 points. Okay, let this be our P0. We can take any point as P0. Okay, now the P pointer is also pointing to P0. Okay, now P, I is equal to 0. At that point, what you do, yes, there is an unvisited point. The point we will visit, we will color it red. Okay, so now we start from here. Okay, so if you see, this point will actually be termed as unvisited. Okay, so this will be visited at the end point. Okay, so now I start from P0. I have to make the value of I is equal to 2 now. Now select Pi, that means I is equal to 2. So select, P is equal to 0 plus 1, which is equal to 1. So I'll now select my P1. So from P0, select the nearest neighbor. Let this be the nearest neighbor. So now this will become P1 because I value is already 1. Okay. Let me just erase this. Okay. So at this point, I was 0. We went inside the loop. Yes, there was an unvisited point. So yes, we went inside the while loop. Now we made the value of I is equal to 1. Now Pi, we have to select the Pi, which is equal to P1. So we have selected the nearest neighbor of P0. Okay. So now mark P1 as visited. Okay, mark P1 as visited or visit P1. Then it will go up and the while loop will execute again. Is there an unvisited point? Yes, there are 4 unvisited points. Okay, basically 3 unvisited points. Okay, so if I see this, now I will become 2. So now I have to select my P2. P2 should be selected from P1, which is its nearest neighbor. So let this be now P2. Okay. At this point, again the while loop will go up. Now, at this point, do we have unvisited points? Yes, we have 2 unvisited points. So what will happen is now I is equal to 2 plus 1, which is equal to 3. I have to select P3 now. P3 should be selected from P2, which is its nearest neighbor. Let this be the nearest neighbor of P2. Once you find it, you have to visit that point, and again the while loop will go up. When it goes up, do we have an unvisited point? Yes, we have one unvisited point. That now I is equal to 3 plus 1, which is equal to 4. Okay, so now we have to find P4. P4 should be found from this P3. So yes, this should be connected like this, and this mark this as visited. Okay, once we have visited all the nodes, okay, this while loop will now terminate and we will come out of the while loop. When we come out of the while loop, now return to P0 from Pn minus 1. Okay, so now at this point we have I is equal to P4. So yes, we have I is equal to 5 actually. Okay, so now we visit. Do we have an unvisited point? Yes, we have one unvisited point. Now I is equal to I plus 1, that is equal to 4 plus 1, which is equal to 5. Now visit this point. Okay, and when we go up again, now I value is 5. At this point, the while loop will terminate. Why? Because there are no more unvisited points. Okay, this is the starting point. We did not visit it in the first step. Okay, we will visit it in the last step. Okay, once we visit it, this while loop will terminate now. Now we have to return from Pn minus 1 to P0. This is P0. And what is the value of I? The value of I, this is actually I minus 1. Okay, they have written it wrong. P of I minus 1, from P of 0 to P of I minus 1. So from P of 4 we will now connect P of 0. P of I minus 1 is equal to 4. So from P of 4, we will connect P of 0. Now this will complete our cycle and we say, yes, this algorithm is always correct when we have to find the robot to our optimization. Okay. So yes,
Excuse me, sir.
yes,
Sir, while starting from P0, it has two nearest points. Then it will choose randomly or choose a
no.
particular.
There, yes, there is where we will come. I will answer this question in the next slide. Okay. So yes, very good question. But this algorithm that we have just now seen is completely wrong. Okay. Because there will be one case where this algorithm will fail. Okay. So yes, that case will be called as its counter example. Now if we find a counter example for the nearest neighbor heuristic, let us find it through this example. Okay. Now if I come to this point, the question that you just asked, who asked this question?
Me, sir.
What is your name? I'm not
Sir,
able to see the
Swayam
screen. Yes, very good question. Okay. This is an excellent question. Okay. This is how you should be thinking. Okay. If you think like that, then see, if you go back to the algorithm, Swayamjyoti, I just want you to answer this. If you come back to this algorithm, do you find a tiebreaker here? That is why the question obviously came to your mind. There is no tiebreaker here. What happens when we have a tie? This is the example. We have a tie here, right? When we start at point 30, now the distance from this is 1. The distance from this, if you take the mod of the distance, then this is also equal to 1. Yes or no?
Yes, sir.
So what will happen? It will start from the first point. It will go from 0 to this. It will go from 0 to, suppose it goes to positive 1. Okay. Next, if you see, the next point is at a distance of 3 and this point is at a distance of minus 1. So are they equidistant? Yes.
No, sir.
They are also equal. Why not? See, 2 will be there here, no? How are they not equidistant?
Yes, sir. Yes, sir.
They are equidistant. 3 minus 1 is equal to 2. And if you see 1 minus of minus 1, that will also be equal to 2. Okay. So yes, their distances are same. So now, which way should it go? Should it go to point 3 or should it go to point 1? Now let the robotic arm starts here. It goes to this point, that is 1. From 1, there is a tie again. There is no tiebreaker given in the algorithm. So it goes to point minus 1. From point minus 1, if I say there is 1 point here, there is 1 point here. Are they equidistant points? Minus 5, minus 1, 3.
Yes, sir.
Yes. 0. Okay. Minus 1, 0. Then there will be a 1, 2 and 3. Similarly, if you see, they are equidistant points. Okay. So my point is that, okay, we will not go and waste time with this example. I hope you understand. So whenever there is a tie and then we have equidistant points, the algorithm that we have just seen will go like a pendulum. That exact thing that we did not want. We told that yes, the robotic arm should not waste from going to one side to another side, from one side to another side. It should not waste its time in this. Okay. So yes, now if you come back to the first slide of today's presentation, I told you two things. There will be a counter example and there should be another algorithm that should produce a better result on this input. Okay, so let us look at one more algorithm. So I say that the algorithm that you can see, a different idea might be to connect the closest pair of points whose connection will not create a problem. Okay, so they have said after the nearest neighbor, now the next algorithm that we are going to see is the closest pair of points. So now they are saying select any point as P0. From here, you find, instead of finding one neighbor, you find two neighbors. Okay. Again, from this point, you go on finding 2 points which form a pair. Okay. So at every point, the size of the algorithm or the size of the path will increase by 1. Okay. So I'm not going into the algorithm. I'm just explaining you the algorithm so that you can understand. Yes. Given this particular example, okay, we will start at point 0. Okay. Now, we will connect 1 and we will connect -1. Okay. So if you see, now from this point, we can connect -5, and from this point, we can connect 3 as its neighbor. Okay. Again, because our algorithm will go like that. Okay. Again, from 5, I can connect -21, -5. Okay. And from 3, I can connect 11. So this is how the robotic arm can go. And from 11, I will connect 21. Okay. So because they're saying that you connect both the endpoints. If this is endpoint 1, this is endpoint 2, yes. This is how the algorithm will work. Now, if you see, this algorithm is preventing the pendulum motion that we are seeing in the first case. So yes, the second case or the second algorithm is a solution to this problem. But again, if I come here, this is also not a correct algorithm. Yes, the closest pair of points it solves this problem. This solution it solves. Okay, but the closest pair of points cannot solve the problem in every case. Okay, there will be a case where this closest pair will fail. Okay, so let us see the counter example for closest pair of points. Okay, so now if the points are given like this, so 2 points are given here. Okay, 2 points are given here. They are given as rows, 2 rows. Okay, and the distance in a row and within 2 rows, these 2 are given to us. This is 1 plus E, and let this distance be 1 minus E. Okay, similarly this will be 1 plus E. This will again be 1 minus E. This will again be 1 plus E, and this will again be 1 plus E. So these distances are given to you. Okay, so let us follow the concept of closest pair of points. Now, you will start at some point. This is the point that you will start at, P0. Now you will connect the closest pair here and the closest pair here. Okay, from this, I will connect this. From this, I will connect this. From this, I will connect this. Okay, so now I told you the endpoints must be connected. So I'll connect the endpoints now. Okay, so this is how the robot will move. If you calculate this value, this will be something like 1C, 1 minus E here, 1 plus E here, 1 minus E here, 1 plus E here, 1 minus E here, and this will be the root over of 1 plus E, 1 minus E whole square. Okay, so yes, if I go through this values and let me take E is equal to 0, nearly equal to 0. When I take this value, okay, this path will be 30% more distance than this path. So yes, if you follow the closest point, this will be the solution that you will get. you can add all these values and take E is equal to 0. You will see 3i more 3i will be there than this value. Okay. So yes, if I just follow the closest pair of points algorithm, then this is my counter example. And what is the correct solution? The correct solution is this. Okay. What we can do is we can go from here, because there is a tie here also and it is unable to break the tie. Okay. So yes, whenever you will have a tie, this closest pair of points and the nearest neighbor heuristic, they will fail. They will fail in different cases. There are different counter examples. I have shown you 2 counter examples. But if you want to find a counter example, you just have to think and prove that the algorithm is incorrect in this case, or it is not efficient. See, if I add all these values and I add all these values, I will see that this value will be obviously less. So why follow this path? Why the robot will follow this path if there is a better path? Okay. So yes, that is why your algorithm is not efficient in this case. And that is why it is wrong. You can show it through a counter example. Now, what can be a optimal algorithm for this problem? Yes, this optimal TSP, which takes a set of points, and for that, what it does, it follows the brute force method. Okay, the given points are 1, 2, 3. What it will do? It will write 1, 2, 3, 3, 2, 1, 2, 1, 3. It will find the distance here. It will find the distance here. Okay. The total cumulative distance. Okay. And then it will compare these distances and it will say that the combination with the smallest distance. Yes, yes.
Sir, your voice is not audible and the screen is not visible properly.
Screen is not visible. Now?
The writings are coming a bit late.
Maybe your net is delayed. Is it happening for everyone?
No, sir. Okay.
So. Yeah, I think so. Your net is a bit delayed. You can refresh your internet a bit. Okay. So, yes, if I just take the optimal case, what will be the optimal case? I have already told this to you. The brute force method. That will take n factorial time. You will write down all the permutations. You will find the... Now am I audible to you clearly?
Yes, sir.
Yes, you will find the cumulative distances. You will compare the cumulative distances in each case. Okay. And whichever is the minimum distance, that you will return. But this will take a lot of time when n is very large. Okay. So yes, this is the optimal algorithm, but this is not always implementable. Okay. Are we above time? No, we still have time. Okay. Now, let us move to the second problem, which says that yes, the formal problem is movie scheduling problem. Okay. So you are an actor. Okay. And the actor has different dates. Okay. He can give a date to a film, but he cannot give dates to overlapping films. He cannot do this film. He cannot do this film at the same time because the dates are overlapping. Okay. So now, if you consider this as a line of intervals, if the intervals are given like this, and you can say that yes, these are a set of overlapping intervals. Okay. Yes, some are overlapping, some are non-overlapping. Okay. So what is the largest subset of mutually non-overlapping intervals which can be selected from I? Okay. If I just change the question, what is the maximum number of movies that an actor can do given these dates? Okay. So given these time intervals, now the question becomes, you have to find mutually non-overlapping. These two are overlapping. This one and this one, they are not overlapping. I hope you understand the concept. Okay. So now you have to find mutually non-overlapping intervals. Okay. So if you find mutually non-overlapping intervals here, so what will be the algorithm that we can do it? So let us look at some of the algorithms that can find mutually non-overlapping intervals. Okay. Now they're saying there are two heuristic algorithms that can be followed. Accept the earliest starting job. So if I just go back, earliest starting job. Among all this, which is the earliest starting job? It is the president's algorithm. Okay. So yes, the actor can do president's algorithm. Once, if he does this, then he cannot just let me do it. If he accepts this movie, then he has to reject this movie and he has to reject this movie. Why? Because they are overlapping. Now after this, also he has to reject this because these two are overlapping. But once he has completed this, now what are the remaining movies? These are the remaining movies. If you see what he can select next, the earliest starting movie, which is Steiner's Tree. Okay. Once he selects this, this has already been rejected. Okay. But he will also reject this. Why? Because these two are overlapping. Okay. And if he rejects this, then he is only left with three more movies. Okay. Earliest starting. He will start the earliest movie. He will reject this movie. And then if you see these two are non-overlapping. So after he completes this, he can take this also. Okay. So this is the concept of earliest job first. Okay. Similarly, if we consider shortest job first, what is the shortest job? He'll accept that job only. Okay. So let us come here. What is the shortest job here out of all these three? I think it is discrete math. Okay. So he'll select discrete math. Okay. And then he has to reject this. Then he has to reject this. Okay. After this completes, then between these two, he will select the shortest job and all other overlapping jobs will be rejected. Okay. So if you consider these two algorithms, so what can be the counter examples for these two? Okay. So yes, I give you this as a homework. Think and come up with counter examples to prove that earliest job first and shortest job first are completely wrong. How you can prove this? You can find one example where this algorithm performs bad and a better solution exists. And you should also find one more algorithm that can find that solution. Okay. So that is the problem that you have to come up with, and I'll give you the answers in the starting of the next class. Okay. So yes. Until then, any doubts regarding this interval scheduling problem? Okay. So we'll start the discussion from here itself. You just try. I'll share the slides. You can try to go through the slides and you can try to come up with a counter example as I have shown for the previous case, which is robot tour optimization. Okay. We'll discuss from here itself. So until then, I think it is already time. So we'll end the discussion here. So thank you for your time and thank you for your patience.
Good afternoon, friends.
Good afternoon, sir.
Good afternoon. Good afternoon to all. So last class we discussed the theory of comparative advantage. We discussed how theory of comparative advantage helps in finding out what is the gain from trade. We discussed how to find out the comparative advantage, and there we discussed if a country or trading partner is producing a commodity at a lower opportunity cost per unit, then the country enjoys comparative advantage over the production of that product. The example we have taken, two countries, India and Brazil, two products, rice and sack. Input matrix given, India requires 2 labor days to produce 1 kg of rice, and Brazil requires 10 labor days to produce 1 kg of rice. India requires 4 labor days to produce 1 unit of sack, and Brazil requires 5 labor days to produce 1 unit of sack. So from the input matrix, it is observed India takes less labor hour to produce 1 kg of rice as well as 1 sack. So India enjoys absolute advantage over the production of both the commodities rice and sack. So in this situation, theory of absolute advantage will not help in finding out the gain from trade, because under this situation, trade is not possible since one country is producing both the commodities and other country is producing none. Then we find out what is the comparative advantage of a commodity enjoyed by a country. So there we find out what is the opportunity cost per unit, and given the input, we can find out the opportunity cost per unit by taking the ratio of two prices. So for India, the opportunity cost per unit of rice is equal to 0.5 sack, 2 by 4, and the opportunity cost of sack for India is equal to 4 by 2 or 2R. Similarly, for Brazil, this will be opportunity cost of rice is equal to 10 by 5 or 2 sacks, and for rice this will be 5 by 10 or 0.5 rice. So observing the opportunity cost per unit, it is ascertained that India produces rice at a lower opportunity cost per kg in comparison to Brazil, and Brazil produces sack at a lower comparative or lower opportunity cost per unit in comparison to India. So India enjoys comparative advantage in the production of rice, and Brazil enjoys comparative advantage over the production of sack. What will be the pattern of trade? Basing on this, first we have to assume India produces rice only. India will take complete specialization in the production of rice, and Brazil will take complete specialization in the production of sack. So if India and Brazil produces rice and sack respectively, or completely specialize in the product over which they enjoy comparative advantage, then India will produce 120 kg of rice and Brazil will produce 48 kg of 48 numbers of SAT. Now, the total production before trade and the total production after trade, we observe the total production before trade, rice is equal to 60 produced by India, 12 produced by Brazil, that is 72. Total production of SAT by India 30 and by Brazil 24. So total will be 30 plus 24, 54 plus after trade, the total production of rice is 120 and the total production of SAT is 48. So here we observe, since the total production of SAT after trade is less than the total production of SAT before trade, so complete specialization will not help in answering the trade between two countries, India and Brazil. If complete specialization is not the answer in this situation, then we'll go for partial specialization. Now, what is the concept of partial specialization? Partial specialization, we say, the country which is efficient in the production of a commodity will also produce the commodity where it has the comparative disadvantage. But it will produce more of the commodity over which it has the comparative advantage and less of the commodity over which it has the comparative disadvantage. Now, in this case, India has the comparative advantage over the production of rice, but Brazil has the comparative disadvantage in the production of rice. And we have the production of rice made by India is more than that of the total production made by India and Brazil before trade. But this was not the case for SAT. And since Brazil is efficient in the production of SAT, let Brazil produce or let Brazil utilizes all the labor hours for the production of SAT. All the 240 labor hours is utilized for the production of SAT. As a result, 48 SATs has been produced. But both the countries require minimum 54 amount of SAT. Both the countries. So how much is required? Before trade, production of SAT is equal to 54. After trade, 48. So minimum requirement or minimum consumption by both the countries is 54. So minimum 54 units of SAT should be produced. So what will be the case? So since Brazil is efficient in the production of SAT, let Brazil produce or engage all the labor hours. So utilizing 240, Brazil produces 40 SAT. So how many requirements left unproduced? So this is 54 minus 48, that is equal to 6. So let India produces both the commodities, SAT and rice. There will be no complete specialization on the part of India. India will produce both the commodities, but more of rice, since it has the comparative advantage over the production of rice, and less of SAT. So how much fat India will produce here? What is assumed? What is the minimum requirement? Minimum requirement is equal to 54 or 6 units. Let us assume India will produce 10 units of fat. Assume you can take 6 units, the minimum requirement, and we are taking, let us say, India produces 10 units of fat. So total production of fat will be 48 plus 10, 58, more than the total requirement of fat before trade. Now, if India produces 10 units of fat, what is the total production of rice? Total production of rice cannot be 120. It will be less than 120. So how much rice India will produce? To produce 10 units of fat, how much labor days India will take? How much labor days India will take? Please, anybody? Anybody, please? So if will not answer, then how I will know that you are clear about the concept? How I will know? Okay, if nobody is coming forward, so let me solve and proceed without wasting the time. Now, to produce 1 unit of fat, India requires 4 labor days. To produce 10 units of fat, India requires 40 labor days. Now, India possesses 240 labor days. Out of the 240 labor days, 40 labor days has been utilized for production of fat. How much is remaining? Remaining 200 labor days. Using 200 labor days, India will produce rice. How much rice India can able to produce utilizing 200 labor days? Production of rice requires, 1 kg of rice requires 2 labor days. Utilizing 200 labor days, India will be able to produce 100 kg of rice. So this is how partial specialization will work. You can take also that let India produce more of such, because if India is producing 100 kg of rice, this is again more than the total requirement of 72 kg of rice. You can assume let India takes 20, produces 20 sacks. For 20 sacks, India will require 100 or 80 labor days. 240, 80 labor days utilized for production of sack. Remaining how much? Remaining 240 minus 80, 160. So utilizing 160, India is able to produce 80 kg of rice. This 80 kg also more than the total requirement of 72 kg of rice. So here trade can take place. So what is the situation? Production before trade and after trade through partial specialization. Partial specialization, what is the total? Total will be 80 kg of rice and 20 plus 48, 68 number of sacks, which is more than the total production and consumption of sack and rice before trade. So now trade will take place. This is the production. The next will come to what will be the consumption or we say trade is taking place, then we'll go to consumption. Trade is taking place. When trade is taking place, first we have to find out what is the terms of trade. How much that will be exchanged against how much of rice. So if we'll take the inequality, the opportunity cost per unit of rice will take 1 R, and this will be India is selling the rice. When India is selling the rice, so 0.5 SAT less than equal to 1 R and less than equal to 2 R. This is the inequality in terms of your rice. Also in terms of SAT will be 0.5 rice less than equal to 1 SAT less than equal to 2 SAT or 2 R. Sorry, 1 R, or it is 2 S, here 2 R. This is the inequality. Let us assume again, two countries decide the terms of trade will be 1 R is equal to 1 S. 1 kg of rice is equal to 1 SAT. That this 1 R is equal to 1 SAT satisfies this condition, also satisfies this condition. Both the conditions have been satisfied. So we assume that the terms of trade is equal to 1 R is equal to 1 S. Now on that basis, we'll proceed further. How much trade will be there? If Brazil requires 12 kg of rice, Brazil can purchase 12 kg of rice. If Brazil will purchase 12 kg of rice, then India will take 12 sacks. India will sell 12 sacks in exchange of 12 rice, or sell 12 kg of rice in exchange of 12 number of sacks. If India will take 12 number of sacks, then its domestic requirement will be fulfilled, consumption will be fulfilled. And if Brazil will sell 12 sacks, then its domestic requirement will also be satisfied. Now, take Brazil is requiring 15 number of sacks. If Brazil is requiring 15 number of sacks, kg of rice, then it will exchange 15 sacks to India. Give 15 sacks to India, and in exchange taking 15 kg of rice. This is the trade between two countries. Now then we'll come to discuss what is the consumption. What is the consumption between two countries? After production, we'll come to consumption. What is the consumption? Consumption will be India is purchasing 15 sacks and in return giving 15 kg of rice. So total rice available for consumption in India 80 minus 15. So this will be 65. Total sack consumed in India, 20 sacks produced by India and 15 sacks imported. So total will be 35. What is the amount of rice Brazil will consume? 15 kg of rice imported from India, produced nil, so total consumption is 15. How much of sat Brazil will consume? Producing 48, selling 15, remaining 33. So just check it whether the total production after trade is equal to total consumption or not. Total production is 80 kg of rice and 68 kg or 68 number of sack. Total consumption of rice made by India 65, made by Brazil 15, 65 plus 15, this is equal to 80. Total consumption of sack by India 35, by Brazil 33, total is 68. So total production will be 68. So consumption and production matches, tallies. Then last step will go to discuss what will be the gain from trade. So already I told you the gain from trade we measure through the difference in consumption after trade and before trade. If we deduct the before trade consumption from the after trade consumption, what we will get is the gain from trade. After trade consumption is equal to 65 here. Before trade consumption is equal to 60. So what is the gain from trade? So this will be 65 minus 60. This is equal to plus 5. Similarly, what is the gain from trade in terms of SAT? Consumption is equal to 35 after trade, before trade 30. So this will be plus 5. So India is gaining 5 kg of additional consumption of rice and 5 additional consumption of SAT from trade. What is the gain to Brazil? Brazil is consuming before 12 kg of rice, right now consuming 15 kg of rice. So this will be 15 minus 12, that is equal to plus 3 kg. What is the additional consumption in terms of SAT? Before consuming 24, after consuming 33. So this will be 33 minus 24, that is equal to 9, plus 9. So your total additional consumption of rice by both countries, that is equal to plus 5 plus 3, 8. So here after trade consuming 80, before trade consuming 72, gain is plus 8 to both the countries. Similarly, in terms of your SAT, before trade consuming 54, after trade consuming 68, so this will be 14. Now, this 14 is shared by India 5 and Brazil 9. Brazil is consuming additional 9 SAT, India is consuming additional 5 SAT, so total consumption increases by 9 plus 5 is equal to 14. So, this is how we can explain the gain from trade utilizing the partial specialization. When we'll utilize partial specialization, first test the complete specialization, and if the total production of commodities are less than the total production of commodities before trade, then you can think of going for partial specialization. And allowing a country to produce both the commodities, then we can explain how trade through comparative advantage benefit both the countries. Now I will take another example. Same example, we can take this rice and sat. To produce 1 kg of rice, let us say this is your India and this is the Brazil. The same figure 2 and 4 I will retain. India requires 2 labor days. We should say labor days required to produce 1 unit of rice and 1 unit of sat. Sat, let us say India requires 4 labor days to produce 1 unit of sat. Brazil, let us say, requires 6 instead of 10. 6 labor days to produce 1 kg of rice and 3 labor days to produce 1 sat. We have now 240 labor days. Same, we are taking equally divided for production of rice and sat. Now this is the question. Now we will proceed further and we will see whether trade can be possible utilizing the comparative advantage. Trade can be possible utilizing the comparative advantage or not. Now, if we observe what we observe, India enjoys absolute advantage in the production of rice and Brazil enjoys absolute advantage in the production of sat. So we are, once each country is enjoying absolute advantage, we will not go to analyze the trade through comparative advantage. We can able to analyze, no problem on that. But since absolute advantage is the basis of trade and using the complete specialization, we can go for the complete specialization and analyze what is the gain from trade. Now I am revising the figure. I am taking it, let us say, I am taking it, let us say this is 2 and 3. One case. Another case, let us assume this will be 3 and this will be 4. Assume. So here, India is producing rice and sat at a lower input cost. To produce 1 kg of rice, India requires 2 labor days, but Brazil requires 3 labor days. So India enjoys absolute advantage in the production of rice. Similarly, for production of sat, India requires 3 labor days, Brazil requires 4 labor days.
Sir, you are not properly audible.
Please, my voice is not audible. Okay, thank you.
It's breaking.
It is breaking us, okay. Is it clear now? Yes, is it clear?
No, sir, it's still breaking.
It is still breaking. I'm taking my mic close to my mouth. Okay, please. It is clear or voice is breaking again?
Sir, clear.
Sir, breaking again.
So, Abhishek occurs. My voice is clear or it is breaking?
Sir, it is clear.
It is clear. So, yes, please check your set. I'm also asking, Ankit, my voice is clear to you or any break is there?
It's clear, sir.
It is clear. So please, yes, check your set. Now, here we are observing India is enjoying absolute advantage in the production of rice and salt, and Brazil enjoys absolute disadvantage in the production of both the commodity. So, we cannot explain trade through absolute advantage. Then we'll go to discuss whether trade is possible with the help of comparative advantage or not. Now, for this, what we have to do, we have to find out what is the opportunity cost per unit. This opportunity cost per unit for India, 1 unit of rice, it has to sacrifice 2/3, ratio is 2/3. 2/3 means 0.767 sat. And for sat, it is 3/2, 1.5 rice. Clear? Now for rice, it will be 3/4 or 0.75 sat. And this will be 4/3, 1.33 rice. Is the figure clear occurs? The opportunity cost I calculated is correct? One is 2/3, other is 3/2. We are taking the inputs. So here we'll simply take the ratio of two inputs. Yesterday I explained you mathematically how.
Yes, sir.
Yesterday I explained. So just calculate 2/3. 2/3 is equal to 0.66 or 67 you can take. 3/2, 1.5. 3/4, 0.75. 4/3, 1.33. Okay?
Yes.
So when I am calculating, please calculate and please give me the support. We can save time and we can proceed further. Okay. Now, given this, which country has the comparative advantage over the production of which product? For rice and for salt. For rice, compare the opportunity cost per unit between two countries.
For India, sir.
India, because India produces rice at a lower opportunity cost per unit because 0.67 is less than 0.75. So for rice, India enjoys comparative advantage. For salt, 1.33 is less than 1.5.
Brazil.
So Brazil enjoys comparative advantage over the production of salt. Now, we'll go to discuss the trade between two countries. We'll go before trade and after trade. I'm going the situation between India is producing rice and salt number and rice kg. Similarly, Brazil is producing rice, kg, and sat. No. First, we'll take production before trade. Production, or I can take, usually we'll take before trade, production, and consumption. Here, how much of two commodities each will produce and consume before trade? We have now 240 labor days. We say equally divided. Here 120, here also 120. Utilizing 120, India can produce 60 kg of rice and consume this 60 kg of rice. Using 120 labor hours, India can produce 40 sats and consume also 40 sats. For Brazil, Brazil will produce and consume 40 kg of rice and 30 number of sats. So we can take another table. What is the total production and consumption? Rice, sat. We'll take before trade and after trade. Before trade, total production of rice, India 60, Brazil 40, 100. Total production of sat, India 40 and Brazil 30, 70. Now let us assume there will be complete specialization. If there will be complete specialization, we will take the situation after trade. We will take complete specialization. With complete specialization, what is the production? Complete specialization means India will produce rice only. Brazil will produce sat only. If India will produce rice only, then the total production of rice will be 120, utilizing 240 labor days. Now, if Brazil will produce sat only, then Brazil will produce 240 divided by 4, 60 sats. So, total production of rice is equal to 120, total production of sat is equal to 60. So, can we say that trade can take place if complete specialization is the basis for trade? Can we say trade takes place when we take complete specialization as the basis? Before trade, producing 70 sats, after trade, producing 60 sats. So here, production of rice is more, but production of sat is less. Since the production of sat is less than the before trade, trade cannot take place on the basis of complete specialization. Because both the countries, they require minimum 70 sats for consumption. But after trade, after complete specialization, only 60 sats has been produced. So when only 60 sats has been produced, then both the countries, if at all there will be exchange of sats against rice, then each country cannot be able to meet their minimum requirement of sats. Brazil is completely specializing and producing 60 sats. If Brazil is completely specializing and producing 60 sats, then Brazil can able to export, sell only 30 sats. Brazil cannot sell more than 30 sats because for own consumption, it has to keep 30 sats. So maximum amount of sat Brazil can able to sell or export to India is equal to 30. But India requires minimum 40 sats. So India will not agree that I will purchase only 30 sats. I require 40 sats. If you give me 40 sats, then I will give you the rice. So here, complete specialization will not solve. Complete specializations will not able to explain the gain from trade. So what the situations, then we'll go for the partial specialization. How the partial specializations will work. So allowing Brazil to produce the commodity over which it has comparative advantage, that is your sat. If Brazil will produce or utilize all its resources for the production of sat, it will produce 60 sats. How much minimum number of sats required to be produced by India? Brazil can give at most 30, but India requires 40. So India must produce 10 number of sats. Minimum. If India requires 10 number of sats to be produced by itself, how much of rice India will produce? For 10 number of sats, India requires 30 labor days. Because to produce one sat, India requires 3 labor days. Out of 240, if 30 labor days is utilized for production of sat, then rest 210 labor days remaining for the production of rice. So utilizing 210 labor days, India can able to produce 105 kg of rice. So what is the production after trade? Production after trade 105 kg of rice by India and 10 sats by India and no rice by Brazil and 60 kg or 60 number of sat by Brazil. So total production will be after trade here will be instead of 120, this should be 105. So instead of 70, it will be exactly 70. Now trade will take place. What will be the rate of exchange between the rice and sat? As your opportunity cost per unit indicates, 1 kg of rice will be exchanged any rate between 0.67 of sat and 0. less than equal to 0.75 of rice or sat. One rice will be exchanged in any rate or any amount of sat that lie between 0.67 and 0.75. Assume Here, one rice will be exchanged against 0.7 sat. 0.7 lies in between 0.67 or 0.75. Assume. Now, if this is the rate of exchange, then what will be the trade? Next, after production, we are coming to what will be the trade. How will determine the trade? India requires minimum 30 sats. So India will import 30 units of sat. Or if you will go for the Brazil side, Brazil will require 40 kg of rice. Now, if Brazil will require 40 kg of rice, how much sat it will give? 1 R is equal to 0.7 S. So 1 R is equal to 0.7 S. 40 R will be 40 multiplied by 7, 0.7, 28 sats. So in exchange, it will give 28 sats. So what is the total production or total sats available for India? 10 and 28, but India requires 40. So the minimum consumption of rice by Brazil will not help India to get this sat if the rate of exchange is equal to 1 R is 0.7 S. We'll take other way. India requires minimum 30 amount of sat. For 30 amount of sat, how much rice it will give? 0.7 S is equal to 1 rice. 30 sat will be how much of rice? 30 divided by 0.7. So this will be 30 sat divided by 0.7. How much we are getting? This is
42.8.
42.8. Okay, thank you. So we are getting 42.8. This is the exchange. We can also approach the same problem in other way. I will approach this. India requires minimum 30 sats. Brazil requires minimum 40 kg of rice. So 40 kg of rice will be exchanged against 30 sats. So what is the one rice? One rice will be 3 by 4 sat, or we can say this is 0.75 sat. So instead of taking 0.7, we can take 0.75 sats. And this 0.75 sats exactly lying in between 0.67 and 0.75 here. Last end we are taking. If we take that, what will happen? Instead of 48, 42.8, this will be 40 sats. Are you? We can approach in so many ways. There is no unique solution for this case. That depends on what is the rate of exchange you are taking. Initially, we are taking 1 is equal to 0.7. We are taking 1 is equal to 0.75. We can take R is equal to 1 R is equal to 0.67 S, 68, 69, any number in between 0.67 to 0.75. Now, after getting the trade, we'll come to discuss what is the total consumption. What is the total consumption? India is producing 105 kg of rice. Out of the 105 kg of rice, India is selling 40 kg of rice. So how much is available for consumption? This will be 65. Producing 105 and selling 40 kg. Remaining 65. What is the consumption of SAT? Producing 10 and purchasing 30. Total will be 40. What is the consumption of rice by Brazil? No production, consuming 40, total will be 40. What is the consumption of SAT? Producing 60, selling 30, remaining 30 for consumption. Now last is your gain from trade. What is the gain? Gain from trade, India after trade consuming 65 kg of rice, before trade consuming 60, so gain from trade will be plus 5. In SAT, no gain, 40 and 40, this is 0. Here for Brazil, this is 0 and this is 0. So in this example, if we'll take partial specialization and if we'll take the rate of exchange between 1 kg of rice is equal to 0.7 kg or 0.75 number of SARs, then we observe India is gaining what Brazil is not gaining out of the trade. So how much gain will be there to two countries? That depends on what will be the total production after trade. Because no gain in SAT that is revealed. Total production of SAT before trade and after trade is same. So when total number of production of SAT before trade and after trade is same, so no gain is possible for consumption of SAT. But gain is there in terms of consumption of rice, because production of rice is more in comparison to the before trade situation. So depending on what is the input ratio, depending on what will be the your terms of trade, how much labor hours are available. So this will indicate whether complete specialization is the case or partial specialization will be the case. When complete specialization is not possible, then we can go for the partial specialization. Usually, when we are taking the comparative advantage, in most of the cases, complete specialization cannot help in analyzing the trade, and there we'll go for partial specialization. With the help of two examples, we can explain how trade makes everyone better off, taking comparative advantage at the basis and partial specialization at the basis of production after trade. The example cited in your book also explained through the partial specialization. Please go through the book. If you find any difficulty, then ask me in the next class. Next class, we will move to the next chapter. If you do not have any doubt, to ask me. We have only few seconds left for us. Already time is completed. So please Again, I request you to go through the book. If you find any difficulty, then ask me in the next class. Thank you all.
Thank you, sir.
Thank you.